with 6-week sprints, and we're putting releases out every 6 weeks. So a lot of the things that you heard Tom talk about earlier, we're practicing in our software development as we try to provide high-quality software in an agile way to our customers. As I mentioned, the topic is static analysis. But the first generation of static analysis was really about 30 years ago with the invention of Lint, and the first version of Lint was available in 1978. And there was a lot of promise with these first generation tools. The notion of being able to find defects as soon as you start writing the code, well, it's attractive because of the cost of finding the defects later and later. Now, the downside, of course, is the reality didn't quite meet the promise. It wasn't targeted towards the type of defects that would really, cause a lot of pain at runtime, things that cause your system to crash or data to be corrupted and those types of issues. And it usually required a lot of tuning. You had to turn on and off a certain set of warnings that were applicable for your kind of code base. In summary, it's too much noise. And in fact, it wasn't the intentions of Lint. The intentions were correct. And in fact, consider this quote from the inventor of Lint as it pertains to noise and relevant defect reports. He said, and this was in 1978, "Lint tries to give information with a high degree of relevance. Messages of the form XXX might be a bug are easy to generate, but are acceptable only in proportion to the fraction of the real bugs they uncover. If this fraction of real bugs is too small, the messages lose their credibility and serve merely to clutter up the output, obscuring the more important messages." So as it turns out, that we had the right goals back then, but we just didn't have an implementation that was suitable to the task. So a number of years passed, and then a new wave of static analysis was introduced into the market. And the focus here was on path coverage, not simply pattern matching at a high level, kind of syntactic checking that was part of Lint. And the idea being push down all the different possible paths through the code, uncover the defects that have real runtime implications, and try to analyze the whole code base all at once, not just a single file or a single function, but do full interprocedural analysis. And so that made a leap forward in terms of the applicability, and in fact, with this type of technology, people could start adopting these tools in their development process. However, there were still some problems. There was still a false positive problem. We'd see false positive rates in 50, 60, 70, 80%. Scalability could be difficult for the more rigorous analysis if you wanted to analyze hundreds of thousands or millions or tens of millions of lines of code, as many code bases tend to be these days. There would be scalability issues. And there really is an elusive sweet spot between trading off getting very good results, real defects in an accurate way, and the scalability of your analysis. So if we can put up the poll results now, we'll see what your view is on what how much you've heard of static analysis. So it looks like a pretty even split amongst folks. You've either tried it or you use it somewhat regularly. We don't have too many power users out there, and so a lot of these issues that I'm talking about is the perfect symptom of the second generation of static analysis. The last question I want to throw up from a poll perspective is, what do you think is an acceptable rate of false positives? As Tom mentioned, false positives it can be the #1 killer of any static analysis solution. And to transition to the next slide, the third generation of static analysis, and this is where we are with Covarity's technology today, we kind of have the best of both worlds. We have solved the problem of scalability to huge code bases while maintaining a very low false positive rate, 15%, and sometimes even lower for certain deployments. So it's comprehensive, it's finding the most critical defects, it's right almost all the time. And we've solved a lot of the integration problems that the initial generations of static analysis kind of fell down from. And so what I want to talk about in the rest of the time here is a particular technology that enables us to deliver this third generation of static analysis. And we call this Boolean satisfiability. We leverage Boolean satisfiability in delivering this technology that helps us drive down the false positive rate. So just to go over these slides at a high level, there's a lot of technical detail behind what Boolean satisfiability does for you, but we'll just give you the high level overview, and hopefully you'll pull away some of the key concepts. So Boolean satisfiability deals with Boolean formulas. Boolean formulas are made up of variables that can be either true or false, and the logical operators and, or, and not. There aren't any, it's a very simple language. There aren't other expressions that you can make outside of those variables of values and those logical operators. And satisfiability asks the question, is a certain formula satisfiable? Meaning, can you assign the values of variables, true and false, such that when you evaluate the entire formula, it evaluates the value of true. And if a formula is satisfiable, there is such an assignment. And if there is no such assignment, we call that formula unsatisfiable. As it turns out, SAT has been used in hardware for a long time. For the folks who are making the tools to enable chip design, Boolean satisfiability is part of Cadence products, Synopsys products, Mentor Graphics products, et cetera, Anyone who's in the EDA space is leveraging SAT. As you can see, a couple of quotes there from executives from those industries. And some of the benefits of SAT solvers, meaning the computer programs that take in these formulas and automatically determine whether or not an assignment is possible, well, they're bit accurate, so all the way down to the ones and zeros, obviously, since we're dealing with true and falses. And when it does come up with a proof, either satisfiable or unsatisfiable, it's exact proof that gives you a complete error trace to the problem that you're trying to solve. You can bound the memory usage so you can keep that scalability in check. And of course, since it's been used in hardware for years, we know it's something that is applicable to very large problems, right? As chips get more and more complex, millions of variables in huge formulas under lots of operations, and we're still going to crank through those. So we want to bring this kind of technology to software so that we can use it to analyze software systems. And the question is, well, if it is so great for hardware, why haven't we been doing that for software for a while? And it's a little bit trickier in the software world because unlike a chip design, which is basically already in that format of ones and zeros, ands, ors, and nots, the gates that make up the chip, and the high voltage, low voltage that you plan on pushing through those gates, software is written in a high-level language, right? C, C++, Java, and so on. And so you need to be able to translate that high-level language into the equivalent formula that could be plugged into a SAT solver. And so just to give you a little bit of intuition as to why that's possible, well, think about each variable in your program. Essentially, it's just an array of bits. So rather than thinking about a variable x or a variable y, we think about that variable as an array of all the bits that are independent variables that make up that particular variable. So x becomes x sub 0, x sub 1, x sub 2, x sub 3, and so on and so forth. And similarly, every expression that you see in a high-level language can be expressed in an equivalent logical formula of ands, ors, and nots. Now, there's an example here on this slide that is the simplest example of the bitwise AND operator, which is just the bitwise AND of each of the elements in the array. But to motivate as to why we can do that for the more complex expressions, we'll take a look at this slide and the addition computation. So if we think back to grade school and how we learned to do addition, and there on the right side, the way we learned is you add up one column, and then you potentially carry the 1, and then you add up the next column, and you carry the 1, and so on. And if you look at how a computer actually performs the addition calculation, after the code's been compiled, that gets into some assembly language, and then that assembly language gets turned into ones and zeros, which eventually get pushed through a processor that specifies that certain instructions should be executed to perform an addition. And this is what that processor would do, right? It would take two operands, A and B, and it would take each bit, A0 and B0, it would push that through a 1-bit full adder, and out would come a result, and then potentially a carry bit would go into the next 1-bit full adder, and so on and so forth, until we've computed the result for the addition. And if you think about it, these 1-bit full adders, well, it's just a sequence of gates. It's ands, ors, and nots, and we're feeding 1 bit at a time through these gates. And so just like we can translate and think about each variable as an array of bits, we can translate